Hey guys, I'm back with another video, and this video is a little bit different than what I have previously shown. This is more of a combination of computer science and neuroscience that I had previously just learned about a couple of days ago, and I thought I would share it with you. And basically, what I'm trying to share is called classification similarity. So classification by similarity. Now, this is a really interesting topic to learn about because the more I started to learn about it, the more I saw the applications for it in our technological lives. Basically, what this does is it takes images in, or it actually can take any piece of data in, and it compares it to already established prototypes to determine which this newly established image is most similar to. And so just to completely, define it, clear cut, let's pull this out, just draw a line. To define this clear cut, this is what it would look like. We have some noisy image that's going in. Let's color code it to this. We have some noisy image that goes in, and it turns into, or it's compared to, and it's compared using some type of a vector metric. It's compared to prototypes. So this would be prototype 1. This would be prototype 2, prototype 3, and then it would keep going. There would be prototypes that are already previously established that serve as kind of something to go off of this. And you might be thinking, okay, noisy image. What does noisy image mean? Let me define that. Noisy image means basically something that is incomplete. Noisy could also mean unestablished or unrecognized. Unrecognized, and other definitions of that sort. And this is an algorithm that is used by computers, and you can think about it, right? If we have, say, some type of an image that is incomplete or has been destroyed via some data failure or whatnot, if you have previously established prototypes, you can help recognize that data and then match it correctly. Similarly, for example, your Face ID on your phone, what I think happens is it takes in this prototype when you initially scan your face, and it establishes that. And every time you have to log in, it compares that noisy or unrecognized image of you to this prototype. And that's why you have multiple scans that it takes initially, right? It takes you, okay, you have to go across the face. So it has multiple prototypes that build up, and you can compare this noisy image to it. So I'll just show you exactly, I'll just give you an example. What's one we can understand? Let's say we have two types of dogs, right? Let's say we have a Samoyed. We have a Samoyed of some kind. And this is a prototype because it's previously established. And we have some other dog breed, let's say Golden Retriever. Right? So Samoyeds are usually more fluffy. They have cute ears. A lot of fur on their face. Oh god, why is it glitching so much? They have a nose. There we go. I have a Samoyed at home. I can't draw one. Uh-oh. That's its nose. And that's its tongue. Alright. Now I have to find how to draw a Golden Retriever. Just give me a second. Okay. After carefully examining what a Golden Retriever looks like, I have finally figured out how to draw one mediocrely. So let's take some type of a gold color and let's draw an abomination. I was kidding, I don't know how to draw. I don't know how to draw a Golden Retriever. That's besides the point. Okay, let's just say this is a dog that is a Golden Retriever. Right? Of course we had to finish its face. right? So these are two prototypes, let's say, right? And what I mean by prototypes is in our database, this is already stored examples of these dogs. So let's say that this is a picture of a Samoyed, so we're going to call it PS. This is a picture of a golden retriever, we're going to call it PG. So now let's say we get this, this new dog is coming into this system. We don't know what breed it is. We know it's either a Samoyed or a golden retriever or some type of mix, but we want to characterize it as either one or the other, right? Let's say this is our noisy image, unrecognized. So this is our noisy, right? So let's see. We have much of this Samoyed hair, but then we have the same Samoyed build, but then we have more snout activity, such as what a golden retriever looks like, right? More of this and more of this, right? And same facial features as a golden retriever, let's say. So we want to classify this as either a Samoyed or a golden retriever, and we're going to call this the picture of an unknown, let's say, or what we usually call an unknown in math, X. So we'll call it X. So this is what happens. How we do this noisy to prototype is what's really interesting in this subject. So now in this stage, this is what we want to do. We want to express this noisy image as a vector. So we're going to express the photos as a vector. And this is a little bit more complicated than it seems, because this is a pretty, it's not something that you would see in math where it's just like one string of numbers or something. It's literal data, and it's in 3 dimensions. So there's a really easy but an understandable way that this could be turned into a vector, and that is that this picture is split up into multiple rows, and each of these rows counts as one vector component. And after that's done, each of the vector components are condensed to make 3 vectors, which shows its position, the vector's position on a 3-dimensional graph. So say this is all split up like this. So let's call this vector for this unknown to be X, by X like this. So each of the components of this vector is like, this is one component, this is one component, so we'll call this 1, this is 2, this is 3, so on and so forth. So it's 1, 2, 3, so on and so forth. For PS, we have the same thing, right? So the vector would be represented as PS, and each of these would be the vector components. Same thing over here. We have this going to be PG. So now, how do we compare it? Okay, we have 3 metrics. We have the vector X, we have the vector PS, and we have the vector PG. What do we do to compare these vectors? Obviously, we found the vectors, which means there's some reason, there's something to do with it. So that's what I'll show you now. Say we create a graph, right? We were able to condense these vectors down into 3 dimensions. And what does that mean? Mainly, we can graph them. So here I am just drawing the axis real quick, trying to make it as straight as I could. Alright, say this is the outward going z-axis, and these are the x and y axes. Let's take x. We condense it down into 3 components to make it 3-dimensional, and let's say that x is in this. Let's pick a color for x. Let's say it's in this maroon color. Not maroon, it's violetish, right? Let's define x to be this vector. Now let's pick PS. Now PS is a different vector, so we're going to represent it in this tealish color. Let's say PS is not this vector. Let's say PS is something like this, right? And then let's say we have PG, and let's have it be in this color. Let's say PG is this vector. So here we have our plot. This is what the computer is going to analyze. So this is also a prevalent thing when using beta diversity plots. If you've done computational microbiology or any other type of data analysis methods, basically what I'm trying to say is that distance, in this case, distance between the vector heads, it represents difference. So the larger the difference, the more difference there is in between the data. So in this case, how are we going to be able to quantify differences? Because if you think about it, we're taking distance between two vectors, so we're going to be getting a distance vector. So that's where, you know, the magnitude comes in. So let's say we determine that, okay, this noisy image, it should be more similar to the Samoyed than it is to the golden retriever. This could be easily represented using a math equation. So that's what I'm just going to write out. If we're assuming, let's say that X is similar to PS. This will be our equation. We're going to have, what is the color we chose for X? This color. We're going to have X minus PS. There should be less distance, there should be less, you know, magnitude of the distance between these two than there should be between X and PG. So when you just look at this equation and see if it makes sense. We're saying that X is very similar to the Samoyed when compared to the golden retriever. And we're quantifying it by saying that there should be less distance between the Samoyed and the noisy image than there is between the golden retriever and the noisy image. And that's what we've accomplished. So at the end, the algorithm will determine that, you know, the Samoyed and the noisy image are the most similar. So X falls under Samoyed. So that is how the data can be classified using similarity. And obviously this is a really cool vector analysis way to think about it. And I'm pretty sure, I also haven't researched much into this, but I'm pretty sure this is how computers do it. This is how many of these algorithms that test for thumbprints might also do it, or Face ID, optometrics, other types of, you know, classification. But the more overlying reason why I was learning this is because there's actually a similar connection to how this works, but in the brain, how the brain is able to classify images and how it's able to determine similarity between other images.